Cycle 4, Lesson 2. In this lesson, we're going to look at more applications of the functions that we've been working on in the course. The focus for this lesson is exponential and logarithmic functions, which are very closely tied to each other. So let's start with an exponential equation. Solving a problem determining the roots of an exponential equation. Lana has purchased a minivan for $24,000. The value, V in dollars, of the minivan is a function of time, t in years. It depreciates according to the function v at t equals 24,000 times 1/2 to the t over 3. Let's just think about this formula for a bit, because if we understand exponential relationships, then we should be able to interpret what this formula is telling us, even without any other information other than that it's money. So we should know that the 24,000 is our initial value, our starting thing. So if we're talking about money, it's the initial value. So $24,000 is what it's worth. The 1/2 is the base. That's the growth rate, or decay rate in this case. So it's 1/2. So when we put that together with the exponent, every time we increase the exponent by 1, then we're going to cut our value in half. So if we had a power of 1 on that 1/2, then we'd have half overall, and a half of 24,000 would be 12,000. So what we need to do or understand, though, is that our exponent is also a fraction. So again, every time we increase the overall value of the exponent, it's going to cut the value of the van in half. So if we have a fraction that's got 3 on the bottom, it means that I need to have a 3 on the top. T would have to be 3 in order for the value of the van to cut in half. So after 3 years, the value of the van would cut in half. And at 6 years, t over 3 would be 2, it would cut in half again. And at 9 years, it would cut in half again. So every 3 years, the value of the van cuts in half. And we can just, if we know how to interpret it, we can see that all we have to look at is the 3 on the bottom, and we'll know that that is our half-life, so to speak. Half-life of the van is, at least the value of the van is 3 years. So how long will it take for Lana's minivan to depreciate to 1/4 of its initial value? Well, 1/4 of its value is actually just cutting it in half twice, isn't it? So just through that little mental exercise, we could probably predict it's going to take 6 years to cut it to 1/4 of its initial value. But let's actually plug the numbers in so that we can play with them a bit and confirm this. So 1/4 of the initial value is $6,000, right? So we want to find t when v equals $6,000. So putting 6,000 in for v, gives me this version of the formula, or this equation. Now I want to isolate t, and I've actually got, we've learned so many different things to do with exponents now that I can actually think of 3 different ways that I can isolate t, just algebraically. That's not even counting using graphs or guess and check. So they all, though, involve simplifying a bit first. So this should have been a 24,000, shouldn't it? I should start by isolating and simplifying as much as possible. So if I divide by 24,000 on both sides, what I get is 1/4 equals 1/2 to the t over 3. Now, I could get common bases, right? I could rewrite a quarter, for example, as 1/2 squared. Right? 1/4 is the same as 1/2 squared. Those are equivalent. Now I've got the same base, and that means that I can just set the exponents to each other. That means that 2 has to be equal to t over 3. And then if I multiply both sides by 3, then t has to equal 6. So that was just using common bases. That works when it's possible, and it is possible, of course, to rewrite a quarter as a half. But, for example, if I look ahead to part B, where I'm supposed to find 10% of its initial value, that one would not work so well, because 10% isn't a nice multiple of a half in any way. But that was one option in this case. So let's call that option 1. In option 2, we could take the log of each side, and that would be from, by the log of each side, I mean at this stage here. That's the simplified stage. If I take the log of each side, then what I get is log 1/4 equals log 1/2 to the t over 3. And then I can isolate t by just reworking this using our laws of logarithms. I could bring the t over 3 down as a multiplication. So we know we can rewrite log 1/2 to the t over 3 as t over 3 times log 1/2. And then I could divide both sides by log 1/2. So if I divide both sides by log 1/2, I would have log 1/4 divided by log 1/2 on the left. And I could multiply, again, let's highlight, that's where that came from. I could also multiply both sides by 3. And if I do that, then I've isolated t, so I just have to type this into my calculator. Assuming my calculator starts. There it is. All right. So, so what was it? It was 3 times log of 1/4. So I'll do the 1/4 as a 0.25, and I have to do that and then hit the log button. And then I'm going to divide that by 0.5 log, so log of 0.5. And as you can see, we got 6 as the same answer. So just typing that into the calculator gives us the correct answer. So that's another way of doing it. Let's indicate our solutions here. And the final way that I could see of doing this, and not necessarily in any particular order, these are just the order that they occurred to me, I could just rewrite in our exponential equation into logarithmic form. So we have this exponential equation, again, starting with 1/4 equals 1/2 to the t over 3. That is an exponential equation. It can be rewritten in logarithmic form. So log of the base, which is 1/2, and the argument was 1/4, and we know that in logarithmic form we're isolating the variable, which was the t over 3. And then we end up, if we use our change of base formula, you might have a button on your calculator that allows you to put 0.5 in as a base, but if you don't, we know we could just rewrite it as log 1/4 using the change of base formula over log 1/2 equals t over 3. And we're basically at the same point as what we did in the last version now. So it turns out to be 2. In other words, what exponent do I have to put on a half so that it equals a quarter? Well, the answer is 2. And then I can multiply both sides by 3, and I get, again, t equals 6. So 3 versions of the same mathematical thinking, really. Okay. For B part, though, we want to find 10% of the original value. So let's do it as decimals. So 10% can be 0.1, and I can rewrite a half even as 0.5 just so I'm consistently using decimals. There's my relationship. As I said, common bases isn't going to work well for this one. Maybe we'll just go to the one where we rewrite in log form. So I'd have log base 0.5 of 0.1 equals t over 3. So then I would type log 0.1 divided by log 0.5 equals t over 3. .32. And again, then we have to multiply by 3. 9.97 if I round it, just barely above 5. So t is approximately equal to 9.97 years. Because remember, we're solving for time here. Solving problems by determining the roots of a logarithmic equation. The time it takes an oven to preheat is given by the formula t, little t, equals 3 log 0.1 big T minus 2 over log 2, where t is the time in minutes, little t is the time in minutes, big T is the temperature in degrees Celsius at which the oven is set. How long will it take to preheat an oven to 350 degrees Celsius? That is giving us big T, and we have to find little t. So in other words, we can just use the formula exactly as given. Little t is going to equal 3 log 0.1 times 350 minus 2 all over log 2. Uh, 350 times 0.1 is 35 minus 2. So we can simplify that a bit. I mean, we could do it all on a calculator at once, but I can rewrite it as 3 log 33 over log 2. So it's a little bit less to type in. 3 times log 33 divided by log 2 is 15.1 minutes. Let's just call it approximately 15 minutes. So, straightforward, just using the formula as given. And B part, if it takes 16 minutes to preheat the oven, what temperature was the oven set for? So in this case, we're given little t and we have to solve for big T. I wonder, I might need a bit more space for this since I'm not using the formula as given. I'm going to do it over here. So 16 equals 3 log 0.1 t minus 2 all over, oops, not that much, this all over log 2. So again, isolating t, isolating a variable. So I can divide both sides by 3. I can multiply both sides by log 2. So 16 times log 2 over 3 equals log 0.1 t minus 2. And that's obviously just going to give me a number that I can then work with. I could leave it as a fraction for now if I wanted to, but I think that would get confusing. So let's actually type that in. 16 times log 2 divided by 3, 1.6055, let's call it. Okay, so we've simplified a bit, but we still have to keep going. We're going to get t by itself. So I have to get rid of this log. Remember, log, that's not a multiplication. It's not log times the bracket, as sometimes people confuse it for. It's its own operation, and the opposite of that operation would be, well, the opposite would be writing it as an exponent, okay? So we want to rewrite in other words, an exponential form. So my base, remember this is a common log, so my base is 10. My exponent is what's by itself, which is the 1.6055. And my argument is the 0.1 times t minus 2. But the beauty of doing this is now I've gotten rid of the log, and I can continue to isolate t. I can now add 2 to both sides, or if you prefer, bring the 2 over to the left, and I can then divide by 0.1, because that'll maintain order of operations. And if I do all that, then I'll know what t is. So 10 to the exponent 1.6055 plus 2 divided by 0.1, which is the same as multiplying by 10, 423 degrees. No, approximately. So probably didn't set the oven to 423 degrees. It was probably sent to 425 degrees. Good pizza cooking temperature. And finally, how many times as intense is an earthquake with a magnitude of 7.2 than an earthquake with a magnitude of 5.6? Well, we've seen this kind of thing before. If I'm not mistaken, we use the letters M for magnitude, so M2 minus M1 equals log of I2 over I1. And I2 over Y1 is what we're looking for. That's the intensity. Or how many times as intense? That's I2 over I1. So it's a single variable the way we're thinking about it, and we're just solving for that. So we put in the larger one is M2 because we need to subtract smaller from larger to have this formula work. And so I have 1.6 equals log I2 over I1. And again, the magic of exponential and logarithmic functions is that we can switch back and forth whenever we need to help us isolate something. And I do want to isolate I2 over I1, so I want to switch it to exponential form. If I do that, being a common log, I got the base 10 again. I put the exponent, which is 1.6, on it, and I've got I2 minus over I1, already nicely isolated. 10 to the 1.6 equals 39.8 times. The stronger quake is approximately 40 times stronger. Okay? Practice, practice, practice.